In this video, we'll talk about calculating the linear correlation coefficient using Python. We saw that a linear correlation exists between two variables if they are correlated and the plotted points can be approximated by a straight line. The linear correlation coefficient R measures the strength of linear correlation between the paired values x and y in a sample. And given a set of pairs of sample data, x and y, R is equal to the sum of, for each data pair, the z-score for the x value in the pair times the z-score for the y value in the pair, add all of those up, and divide by the sample size minus 1. We saw that the value of R is always between -1 and +1, that a value close to +1 shows a positive correlation, and a value close to -1 shows a negative correlation or suggests a negative correlation. And a value close to 0 shows there is no linear correlation. Recall that we both find the value for R, and then we use hypothesis testing in either a table, or in this case Python, to determine what R actually tells us, if this is statistically significant or not. So here's the example we looked at previously. Is the length of a shoe print linearly correlated with height? We have 5 ordered pairs of shoe print lengths and heights in centimeters, and we're saying, okay, is there a linear correlation between these two values for individuals? So previously we did this by hand, and we found a value for R based on that. Now we're going to do it using Python. First, we're just going to plot the scatter plot. So that scatter plot that you see to the right was done using Python, and that's just using matplotlib and scatter. So remember that we can put in x and y as ordered lists, and then we can make a scatter plot. We can give it labels and a title, and then we get this nice scatter plot of ordered pairs of points. So how about for finding R, the correlation coefficient? So there's just one line of code that does this for you. It's just this right in here. I've also printed it just so that we get an output. So scipy.stats.pearsonr xy, whatever your variables happen to be. And so that will do it all for you. And when you print that, it gives you two outputs. It gives you R, so the first value it outputs is R, and the second output that it gives you is the P value. So here we see that R is equal to 0.591269, 0.591269, and that goes with what we had before. Previously, we had calculated R equals 0.591, so this is just a little more precise. And so that is the value for R for this set of 5 paired values. So this is positive. This suggests a positive correlation between these two values. But now we need to check to see whether this value is actually significant. And we don't really have to do any extra work because we already have the p-value. So this is a two-tailed test. We're testing the claim that there is a correlation. The null hypothesis is that there is no linear correlation, that the true correlation coefficient rho is 0. The alternative hypothesis is that there is a linear correlation, that the true correlation coefficient rho is not equal to 0. And so we're saying, okay, what is the probability of having R equals or R greater than or equal to 0.591269, given that the true correlation coefficient is 0? What is that probability? And this p-value is exactly that probability. This p-value is 0.29368. So there's like almost a 30% chance of that happening. Whatever our cutoff point is, usually we'd use like 0.05 as our cutoff point. We see this is clearly much larger than our cutoff point, and so this tells us we do not reject the null hypothesis based on this data. So based on this data. we only have 5 data points. If you recall from the table, the kind of threshold for rejecting the null hypothesis decreases as the sample size increases. So here we only have 5 data points, and we don't have a strong enough value for R in order to tell us that we can reject the null hypothesis. Okay, so what about if we have a larger set of data? So here is actually the full data set of 40 ordered pairs of data set of people's shoe prints and their length and people's actual heights. And so here is that data plotted, again using Python. And so now let's do the same exact thing. We have our ordered lists of data, X and Y. So these are all the X values, all the Y values. Here I've just input them by hand, but of course if you have a file to read from, a comma-separated values file or an Excel file or whatever, you can use Python to read that file as opposed to typing them in manually. And so then I'm going to use that magic line of code to give me the Pearson R, the correlation coefficient R. And this gives me, again, 2 different values. This is R, and it's telling me that R is 0.81213 in this case. And it also gives me the p-value. So this p-value, 2 point blah, 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 e to the negative 10. So that's 0.000, like lots of zeros. There's, we move the decimal point 10 places, so there's 9 zeros and then a 2. This is a very small p-value. And so this is a statistically significant result. How significant? What it's saying is that the probability of observing a result, at least this extreme, the probability that R is greater than 0.81213 or R is less than negative 0.81213, given that the true value of rho equals 0 is super low, is 2 times e to the negative 10. So it's saying the probability of that result, like in the tails, is incredibly, incredibly, incredibly tiny, and therefore we reject the null hypothesis. What does that mean? We're rejecting the hypothesis that there is no linear correlation between shoe print size and actual height, and so therefore this is evidence that there is a linear correlation between footprint length and height, which totally makes sense.